Okay, 6.3 Riemann sums and the definite integral notation. Okay, we're still considering the area under the curve just like we were last time, but we're trying to get a more definitive or a more accurate answer for the area under the curve. So let's consider this curve over here. Okay, if I was trying to find the area under the curve, if I use the Riemann sum approximation, I would divide it into rectangles and add up all the rectangles, and I would get a decent approximation. Okay, depending on the number of rectangles, my accuracy will increase the more rectangles I have. So I'm trying to consider the situation as if n is the number of rectangles, what happens when n approaches infinity? I should get a super exact value for the area, and that's what we're considering right now. Okay, so I'm going to imagine this is my curve f of x. There are n subintervals on a to b. I don't have an a and b, so let me call this a. I'm going to put b over here. Okay, if I want the area under the curve, I'm looking from here to here, and I'm trying to find all this stuff. This plus this plus this, although that bottom part should be negative. Okay, Riemann sum means I'm going to split this into rectangles. Okay, I actually want us to split it into an infinite number of rectangles, which I can't do in real life, but just imagine I'm splitting these up into super skinny rectangles, as small as I can make them. And then once I find the area of all these rectangles, I'm going to add them up or find the sum, and that should represent the area of the curve under the curve from A to B. Okay, so we're going to use this picture to ponder some of these things. Okay, the first question is, if I want to find the area of each of these rectangles, I need the base and the height of each rectangle to find the area. So I'm going to find the width of each rectangle, which is this little teeny distance right here. I'm going to call that delta x. Okay, and I want to consider that in terms of a and b. Okay, so I want to figure out how big each of these little intervals are. They're all equally spaced, so they're all the same. So let's find the total distance from here to here. In the x direction, the total distance would be b minus a. Okay, and then I want to divide it by the number of rectangles I'm splitting it into. So the base of each of those rectangles, delta x, is going to be b minus a over n. Okay, now the question is, what is the height of each of these rectangles? Okay, well, the height lands on this curve. So I'm going to plug the x value of the rectangle into f of x, and I'll get the y value there. Now, if I'm doing approximation, it makes a difference whether I'm using the left, the right, or the middle. But I'm going to imagine n is approaching infinity. If n is approaching infinity, then this expression is approaching 0. So each of these bases of these rectangles is actually infinitely small. If this is an infinitely small width, then it's not going to matter whether I'm coming from the left or the right in the middle, because it's so small that they're essentially the same value. So I'm going to say that the height of each of these little rectangles is going to be f of x, but it depends on which rectangle I'm on. So I'm going to say x sub I. And I'm saying that's x sub I. So if I'm on the first rectangle, the height might be a. If I go to the next one, it's going to be up here. It's just going to depend on the x value at each of those points. Okay, so now we want to think about what is x sub I? How can we do that in terms of the a and the b? Okay, well, if I'm on the very first rectangle, the x value I'm going to plug in is going to be a, because this is so infinitely skinny that it doesn't matter left or right. I'm just going to start with a. Now I'm going to move to the next rectangle. The next rectangle, the x value is going to be delta x away. So if I add delta x, I'm going to get to the next rectangle. Okay, and then I would take this x value and I'll plug that into f and I'll get the height there. Okay, now if I want the next rectangle, I'm going to add delta x again. And then I'm going to take the expression, I'm going to plug it into f, and I'm going to get the height there. So depending on which rectangle I'm on, I'm going to keep adding delta x. So I'm going to do delta x times I to get the ith x value that I'm going to plug into f in order to find the height of each of these rectangles. Okay, now what is my goal here? I'm actually trying to add up all these infinitely skinny rectangles to get a representation for the area under the curve of f of x from a to b. Okay, so I'm going to use summation notation. And then I'm going to write it a few ways using the information we just figured out there. Okay, so I'm trying to figure out what's happening as n is approaching infinity, meaning the number of divisions, the rectangles, or the x-axis is divided into n subintervals where n is approaching infinity. Now I want to add up all the rectangles from 1 to n. To represent summation or adding a bunch of things, I use this symbol. That symbol is the summation symbol. It means I'm going to add up a bunch of things and I need to tell it what to add up. So I'm saying I want you to add up, start with the first rectangle, I equals 1, and add up the area of all the rectangles until I get to n. In this case, n is approaching infinity. Okay, so this is saying sum it up. So I need to, what am I summing up? I'm summing up the areas. So the area is going to be the base times the height. So from above, one way to represent that is to say I'm doing the base, delta x, this is my base, times the height of my rectangle, which we could represent as f of x sub I or something like that. Okay, let's look at it again. N is approaches infinity. N is approaching infinity. This is saying add up from I equals 1 to n the areas of all these rectangles and then see what the result is. Okay, now I'm going to rewrite this a little bit using some of the information we figured out from above. Okay, the first thing I know is that I could represent x sub I as this expression. So I'm going to plug this in here. It's still the same. I know they're the same. I'm just going to replace it. No, that shouldn't say n, that should say k. Not k, I. I used I in this expression. Okay, I used I here. Sometimes they use k. They can actually use any letter they want. You just want to make it consistent with what you've written. So this is delta x times, instead of saying f of x sub I, I'm going to say f of this because they're the same thing. Okay, now since this is the same as this, I'm going to do one more substitution because I want this to be in terms of b, a, and n, because that's normally the information I have. Okay, so if I go back up to here, I know that delta x is the same as b minus a over n. So I'm going to change delta x to b minus a over n and delta x to b minus a over n. Okay, and then that's delta x times I. Okay, now I know that looks like a mess, but I'm going to just show you with numbers what that would look like so it can make a little bit more sense. Okay, so these three expressions are all the same. Okay, I'm going to represent the area of the curve under the curve of f of x equals 3x plus 1 on 2 to 6. Okay, the reason I find this format useful is because that's normally the information given. So since it's going from 2 to 6, my a is 2 and my b is 6, which is in this formula, so I have that information already. Okay, so let me rewrite this, even though I know it doesn't make any sense yet. I'm going to rewrite this. So this is the limit as n approaches infinity. I'm representing the area under the curve in summation notation. Okay, now it says do b minus a over n. Well, my b is 6, my a is 2. So 6 minus 2 is 4 over n. Okay, and then I'm going to multiply it by f, parentheses a plus b minus a over n plus I. Okay, actually I'm going to write this on the side real quick. let me think about this. So I'm doing f of a. What is a? A is 2 plus b minus a over n, which 6 minus 2, I already figured out that was 4 over n, times I. Okay, now I have all the information here, but now it's saying plug it into f. So I want f of 2 plus 4 over n times I. So my f function is over here. So where the x is, I'm going to substitute in this expression. So it's 3 times that expression plus 1. So times, actually I think I'm going to put in parentheses, 3 times 2 plus 4 over n times I plus 1. Okay, and then this summation notation is representing the sum of the area under the curve, because this is the base of each of the rectangles, this is the height of each of the rectangles, and this is saying divided into infinite rectangles. Okay, now that we've established summation notation and what the area looks like using summation notation, which is like this or like this with the b and the a, there's an alternate format called integral notation, or the definite integral notation, where we can write a representation of the exact same expression. So I'm going to use an integral. The symbol for integral is this. It kind of looks like an S, but not really. Okay, on each end of this thing, I put the lower and the upper bound of the limit. So because most of the time I'm going from A to B, I'm going to put A and B. Okay, this is the upper limit, lower limit. Okay, I'm going to write f of x, because that's my curve, and then next to it I'm going to write dx, which is the same as delta x. Okay, now this notation is really nice looking, and it's really saying exactly what this expresses, except this is so complicated looking. So this is saying find the integral of f of x dx from a to b, or it's saying find the area under the curve of f of x from a to b, which is what we want to do. Okay, this is a nicer way to write it, and in the future we will also find better ways to evaluate this, which is another reason we want to be able to go back and forth, because if we see something like this, it's possible we can evaluate it using the definite integral and make it an easier problem for us. But for now, we're just going to practice going back and forth, and that's going to be enough work for us for now. Okay, so for example 1, it says rewrite the definite integral using summation notation. So they're giving it to me in this notation. They want me to rewrite it like this. Okay, and they are equivalent expressions, so I should be able to do that. Okay, so I want to rewrite it with summation notation, so let me do the limit as n approaches infinity. I'm going to go with I equals 1 to n, although you could also use k. Okay, now let's look back at the formula. It's saying do b minus a over n. Well, what's b and a? B is the upper limit, a is the lower limit. So this one, b, this one, a. Which means b minus a over n is 4 over n, and remember that's representing the width of each of the rectangles. Okay, now I want to do f of a plus b minus a over n times I. Okay, let me do this off to the side so I can think about it, because this one's normally trickier. F of a plus b minus a over n. b minus a over n was 4 over n, so I'm going to put 4 over n times I, which doesn't look bad, but I'm doing f of 2 plus 4 over n times I. what is f? Okay, well, f of x is whatever is here next to the dx. So this is my f. So I'm going to take the 2 plus 4 over n times I and plug it in for x right here. So I'm going to have this thing squared minus 3. So let me do this thing squared minus 3. Okay, and then this is representing the width of the rectangle, the height of the rectangle, and this is adding up all the rectangles, the infinite number of rectangles to represent the area of the curve, which is exactly what this notation is also saying. Area under the curve from 2 to 6. Okay, let's consider one more like that. Okay, they gave me the definite integral notation. Okay, let's see. What do I want to figure out first? Let me set it up and then we'll see what we need to find. Oops. The limit as n approaches infinity, I equals 1 to n. Okay, what do I want to do first? I want to do b minus a over n. So e minus 1 over n. Okay, so e minus 1 over n, except. That's the width of each of the rectangles. Okay, now I want to find the height of each of the rectangles. So I'm going to do f of the first term, which is a, plus b minus a over n, which I already figured out was e minus 1 over n, and then times I. Okay, now the question is, what is the function? Okay, the function is whatever this is. So this is the ln of x. So I want to do the ln of this. And that's going to be the height of each of my rectangles. So this is times the ln of that. Okay, this is the base of each of the rectangles. This is the height, and this is adding up the infinite number of rectangles, which is the same as what this is saying as well. Okay, now what if we want to go backwards? So in this case, they're giving me a Riemann sum. I want to rewrite it as a definite integral. Okay, so I know it's going to look something like this. So what do I need? I need a, b, and I need the function. And then I have all the information I need. Okay, so I kind of have to look at this. So this is looking like, this is the ln of a plus b minus a over n, and then this is probably the b minus a over n. Probably? Okay. So I'm guessing that this is a. And there's more than one way to do this that would be equally correct. Okay, so if I'm going to guess that this is a, okay, then I'm going to get, then this should be b minus a over n. This should also be b minus a over n. So if b minus a equals 5, then it must be that b is 7. Let me see if that makes sense. So this is a, b minus a is 5 over n times I, and then this is 5 over n. Okay, so let me at least write that in. So I think it's going from 7 on the upper limit to 2. Now what's the function? Okay, well this is the a plus b minus a over n times I. So the question is, what am I doing to that? Well, I'm doing the natural log of that, which means that f of x is the natural log of that. So this is going to be the natural log. And then I'm doing dx, which you can think of that as the width of the rectangle. That's my dx right there. Okay, so this is the integral notation of this Riemann sum. There is other ways to express it that would also be correct, and we'll look at that probably in the next examples. So let's try the next one. Okay, it's given in summation notation. Let's see, what do I see? I see it's approaching infinity. I see this weird square root thing. 3 plus 4 over n times k times 4 over n. So I'm thinking that this is my b minus a over n. Seems reasonable. Okay, so I know b minus a is going to be 4. What do I think my a is? What am I doing? We're square rooting this plus 4 over n times k. So this is probably my a. or that's one way to set it up. So let's say A is 3. Okay, if A is 3 and B minus 3 is what? 4? Okay, let's see if this makes sense. So B minus A over N, 7 minus 3 is 4 over N. I'm doing A plus B minus A over N times K. Okay, so this is what I plugged in, is this expression. What did I plug that into? I plugged this expression into the square root. So it looks like my function was the square root of x. So this is going to be square root of x, and then it's going to be dx, and it's partly because this is the width of the rectangle. Okay, let's try C now. So this is given in summation notation. I want to rewrite it in definite integral notation. Okay, so let me look at this. I see a 6 over n, so that's probably by b minus a over n, and this is my quantity squared, some kind of function. So one way to look at this is to say maybe this is a. Okay, let me see, a is 4, so let me put a 4 here. Let's see, this must be b minus a over n, so b minus a has to equal 6, so b is 10. And then let me look at this. So b minus a is 6 over n. Then I have a plus b minus a, 6 over n times k. And then what am I doing to it? I'm taking the whole quantity and I'm squaring it. So my function is going to be x squared, which is kind of like the height, dx, which is the width of the rectangle, infinitesimally small. Okay, that definitely works. Is this the only way that works though? No. I could change this and make another integral that also works. So let me just revisit this. No, just this one. I won't do it the other one. Let's look at B. Let's look at C again. Okay, say I want to do a different integral, but I want it to be the same. Okay, let's say I want to make A 0. Let's just start with 0. Okay, if I want to make A 0, B minus A over N still has to equal 6. So this must be 6 then. Okay, 6 minus 0, 6 over N, and then this would be b minus a over n times k. This still works. Okay, but what about my function? Okay, if I do this, a is now 0, so I'm doing 0 plus 4 plus b minus a over n squared. So 0 plus b minus a over n squared is really just 6 over nk. So if I plug in 6 over nk, I'm doing 4 plus, 6 over nk, and then I'm squaring it. So this would mean that my function is 4 plus, and then I plugged in this 6 over nk, and then I squared it. Okay, I'm going to look at this and see that this is actually the same, representing the same summation. Okay, so 6b minus a over n, 6 over n. If I plug into this function 4 plus, instead of a, I plug in 0 plus 6k over n, I get this, and then I square it. So these would give me the same result, and they represent the same area under the curve. So there's more than one way to represent this. Sometimes on a multiple choice, they'll give you some options, and you just need to see which one works. Okay, one more example. Okay, write an integral to represent the given limit, assuming the lower limit a equals 0. Okay, so they didn't give me the sigma notation, but this is a sum, and n is approaching infinity. So they're just giving it to me as a sum. They're adding the restriction that I want the lower limit to be a equals 0. Okay, so let me see. This is going to be this. They told me that a is 0, so this has got to be 0. Okay, now let me look at this and try to figure out b probably. So I have 2 over n times this giant summation. So this is probably my b minus a over n. Okay, what is A? A is 0. So B minus 0 over n, this must be 2. 2 minus 0 over n. Okay, now they're giving me this in summation notation. So the first thing I'm plugging in is 2 over n. So let me see where I am plugging 2 over n. For the first expression, I'm plugging 2 over n right here. Okay, so this looks like it's 1 over 2 over n plus 3. Okay, and I'm plugging in 2 over n because that's the first term. So this is going to be 1 over this plus 3. So my function looks like it's 1 over x plus 3, and then I'm going to put dx because that's the width. Okay, does this work? Let me see. So for the first term, I got 2 over n, 1 over 2 over n plus 3. For the second term, I would do 2 over n times 2, which is 4 over n. So 1 over 4 over n plus 3. For the third term, I would do 2 over n times 3, which is 6 over n plus 3. For the last term, I'm doing 2 over n times n, and then I'm plugging into 1 over x plus 3. Okay, had they not added the restriction that a had to equal 0, I could have had a different representation, integral representation for the limit as well.